Hello everyone. Let's begin with something you've all felt. Ever tried stopping a moving football with your hands? A light tap on a stationary ball is easy, but a fast moving one almost knocks you down. Why? That's because of momentum. For a particle of mass m moving with velocity v, its momentum p is equal to m times v. Momentum is a vector, which means it has both magnitude and direction, always aligned with velocity. The unit is kilogram meter per second. Momentum is what gives motion its punch. The heavier or faster the object, the harder it is to stop. Now, Newton gave us a deeper connection. He said force is not just mass times acceleration, more generally, it is the rate of change of momentum. That is, force F equals dp by dt. If mass is constant, this reduces to the familiar F equals ma. But the broader form is powerful. It works even when mass changes, like in rockets ejecting fuel. So Newton's law in momentum form is the foundation for extending motion analysis to entire systems of particles. Imagine not one football, but a whole team running in different directions. How do we describe the motion of the group? We add their momenta vectorially. For n particles, the total momentum p equals p1 plus p2 and so on up to pn. Each p, I is m, I times vi. The equivalent form of total linear momentum is p vector equals m1 v1 vector plus m2 v2 vector and so on up to mn vn vector. This total momentum tells us how the system, as a whole, responds to forces. It doesn't matter how complicated the individual parts are, their contributions simply add up.
Here comes a beautiful link. Recall that the velocity of the center of mass, v, is equal to 1 over m times the sum of mi vi. Multiplying through by the total mass, m, gives p equals m times v. That means the total momentum of the system equals the total mass multiplied by the velocity of its center of mass. So instead of tracking every particle, we can just watch the center of mass. It represents the momentum of the entire system.
Let's push further. Differentiate p equals mv with respect to time. We get dp by dt equals m times a, where a is the acceleration of the center of mass. Now recall our earlier law for motion, ma equals f external. Substituting, we arrive at a powerful statement, dp by dt equals f external. This is Newton's second law extended to a system of particles. It says that only external forces change the total momentum of a system, internal pushes and pulls cancel out. Now the magic happens. If the external force on the system is 0, then dp by dt equals 0, which means p is constant. This is the law of conservation of linear momentum. In symbols, momentum equals constant when external force is 0. Even if particles collide violently or follow complicated paths inside, the total momentum of the system remains unchanged. In scalar form, each component px, py, pz is constant too. This principle is one of the most universal laws in physics, holding true from subatomic reactions to planetary motion. Let's see this in action with a nuclear example. A radium nucleus decays into a radon nucleus and an alpha particle. Step 1. External forces are negligible. Step 2. By conservation, momentum before decay equals momentum after decay. So in the laboratory frame, the center of mass continues along the same straight path as the original radium nucleus. In the COM frame, however, the radon and alpha particles shoot off in opposite directions, back to back, with equal and opposite momenta. This is why the law of momentum conservation is trusted even in nuclear and particle physics. Now let's leave the atom and fly to the stars. Binary star systems consist of two stars orbiting each other. If no external forces act, their center of mass moves uniformly like a free particle. In our Earth-based frame, Their trajectories look complicated. The COM drifts while the stars orbit around it. But in the COM frame, it looks simpler. The stars move in perfect circles, diametrically opposite to each other. This trick, separating COM motion from internal motion, is what makes celestial mechanics manageable.
So to wrap it up, the total momentum of a system is the vector sum of all particle momenta. It can also be written as total mass times velocity of the center of mass. Newton's second law for systems says dp by dt equals F external, and when no external force acts, momentum is conserved. From exploding nuclei to colliding cars, from firing rockets to orbiting stars, this principle unites the small and the vast under one universal law. I hope you now see momentum not just as a formula, but as a bridge that links the microscopic world to the cosmos. See you in the next session, where we'll continue exploring the beauty of rotational motion.